Welcome everyone for our N3AS seminar. Today we are very pleased to have Professor Tracy Slatyer from MIT. She will talk about a status update on Galactic Center GeV gamma ray access. Over to you, Tracy.
Thanks very much for the invitation and the introduction. I'm very happy to be here. I hope I'm not drawing anyone away from voting in the election. You know, if you can and you haven't already, I think it's good to exercise that civic duty and responsibility. I just became a US citizen a couple of months ago, so I have duly voted in my very first US election ever. All right, but today I want to tell you about what's been happening with studies of the Galactic Center gamma ray excess from the inner galaxy. So I want to begin by I know that, not everyone here has been following this story for the 13 or so years that it has been around. So I want to start by telling you, what do I mean by the Galactic Center excess? What is the history and some of the properties that we think we know about this excess? And then why am I talking about it? Well, it's gotten a lot of interest in the field as a possible signature of either dark matter annihilation or a new population of pulsars in the inner galaxy. Then I want to talk about how might we distinguish these hypotheses or show that it's something else altogether. And there are sort of three major axes on which people have thought about distinguishing these things: the morphology of the signal, the granularity of the signal, and looking for counterparts at other frequencies. So I'll try to give you a status update on each of those things. For some of these, I'll talk about my own studies, but I'll try to give a more general picture of what the status is in the field. If people want to know more detail about the stuff that I personally have worked on, I'm happy to talk about it in the questions and discussion afterwards. And then I'll wrap up with the summary and outlook. Although I'll tell you at the moment that the punchline of this talk is that I'm not going to, at the end of the talk, being like, it is clearly pulsars or it is clearly dark matter. To me, this is still... There have been some strong claims in this area, but for me at the moment, it still looks like an uncertain area where we could benefit from both more data and more better analysis tools. Okay, so let me just jump straight in and tell you what I'm going to be talking about. So the Galactic Center excess is a feature in gamma rays from the inner part of our Milky Way galaxy. It's been observed in public data from the Fermi Gamma Ray Space Telescope, starting by Goodenough and Hooper in 2009. It was confirmed by the Fermi collaboration in an analysis in 2016, and it has been confirmed by many other groups in the interim. Spatially, it looks like a blob in the center of the galaxy, peaking strongly towards the center of the galaxy. This is from an old paper by Abazagian and Kaplinhat in 2012. And as you can see, it looks like a blob. It looks here like it's only within about the inner degree of the galaxy, but it's shown to extend out about 10 degrees from the center of the galaxy, which is about 5,000 light years at high confidence. Energy-wise, it peaks in gamma ray photons with energies between about 1 and 3 GeV. It has a fairly broad spectrum. This lower plot is showing the extracted spectrum of the excess. These error bars are statistical error bars only. So this is power per logarithmic interval on the y-axis, energy on the x-axis. And this is one extraction of the spectrum of the excess without systematic error bars. Now, the reason that this excess has been of great interest to particle physicists, because this turns out to be actually very similar to the signal that you might expect to see if dark matter particles were colliding with each other in the inner galaxy, producing standard model particles, which subsequently hadronize and decay, producing gamma ray photons. This solid line on this plot is a fit of a dark matter model. I think this one is dark matter annihilating into B quarks and anti-Bs, but you can get similar results for annihilating into other quark species. And you see it goes nicely through all the data points. And interestingly, you can infer from this one annihilation rate you need to fit the data, and it comes out to be an annihilation cross-section of about 2 × 10 to the minus 26 centimeters cubed per second. That is an important number for people who are used to thinking about dark matter, because if you had that annihilation cross-section in the early universe, it would naturally, if the dark matter was ever in thermal equilibrium with the standard model, that annihilation cross-section would deplete its early abundance to the level that we observe today. So this is not like a guaranteed expectation of a dark matter signal, but if this did actually turn out to be from dark matter, it would also give us a really simple explanation for why we observe the observed amount of dark matter in the universe. At the same time, there's another competing strong astrophysical explanation, which comes from the fact that all these dashed and dotted lines in this plot are observed spectra of populations of pulsars, especially millisecond pulsars in gamma rays in our galaxy. So pulsars are spinning neutron stars. They radiate over a broad range of frequencies. And Globular clusters are expected to be pretty rich in pulsars. By observing globular clusters and millisecond pulsars seen by Fermi, we get these spectral curves, and you see they look pretty close to the data for the galactic center excess. There is a discrepancy at low energies, but that's not significant once you take systematic uncertainties into account. So this signal's been around for about 13 years. The signal itself is extremely statistically significant. The last time I actually counted the photons in it, it was well over 100,000 photons. It's probably more than that by this point. It's clearly not a statistical fluctuation. The question is what's causing it. I should also say, I don't know what your convention is usually for asking questions during the talk, but I am happy for people to ask questions during the talk if you would like. Okay, so if this was a dark matter signal, it would be completely transformational. This is my obligatory dark matter motivational slide for people who don't spend all their time thinking about dark matter. We have pretty good evidence that roughly 84% of the matter in the universe is something that we don't understand. We call it dark matter because it does not interact with light at a level that we have yet reliably detected, but maybe this galactic center excess is the first signal. There are multiple lines of evidence for the statement that there is some component of the universe that has mass and gravitates, but doesn't interact at levels we have yet firmly detected with the known particles. And so far we've only detected it by its gravitational pull on the visible matter that we can see. What we've learned from looking at it, from mapping its distribution through the universe, is already enough to tell us that there are no really good candidates for the dark matter in physics we currently understand. So it's potentially one of our biggest clues to what might lie beyond known physics. There's a huge multifaceted program to look for possible signals of dark matter interacting with standard model particles. We don't know what the dark matter is, and there are many options for what it could be, but there is a broad class of scenarios where the dark matter was once in thermal equilibrium with the standard model and was depleted through collisions of dark matter particles that produce standard model particles. And if that's what set the dark matter today, from the present day abundance, you can infer the annihilation rate in the early universe. If the annihilation rate was higher than this number, we would have less dark matter left today. If it was less efficient, we would have more dark matter left today. And so that benchmark annihilation cross-section is this 2 to 3 times 10 to the minus 26 centimeters cubed per second number that I pointed out in the previous slide. So the galactic center excess, if it is dark matter, it's just a coincidence that the spectrum looks like pulsars. If it is pulsars, there's a bit of a coincidence that the normalization looks like what you would naively have expected from these simple dark matter models. So obviously, when you see something like this, the obvious question is, all right, so if we have multiple good hypotheses that could explain this result, how are we going to tell the difference? I mean, especially if we think it might be dark matter, extraordinary claims require extraordinary evidence. We would really like to eliminate the other possibilities and find some confirming signals. So how might you tell these apart? Well, one way is to look at the overall morphology of the signal. I said that it looks like a blob peaked at the galactic center, which is rather imprecise. More precisely, if you look at simulations of dark matter halos, we expect the inner region of the dark matter halo to be roughly spherically symmetric. We typically model it in these analyses by a modified Navarro-Frank white density profile, which you can think of as just being like a power law with respect to distance from the galactic center. Now, the distribution of pulsars is more uncertain. If these are pulsars making this excess, they weren't predicted in advance. Their distribution will depend on exactly what is the mechanism that is producing them in the inner galaxy. There have been proposals for production mechanisms that could give a more spherically symmetric distribution, but it's also reasonable that a pulsar population could trace other galactic stellar populations, in particular the stellar bulge. And there have been claims in the past, which I'll say a bit more about later, that the excess really does trace the stellar bulge of the galaxy. And if that was confirmed and robust, it would be a good argument that we're looking at some kind of stellar population. So that's one direction that you can go at to try to distinguish these. Another is to say, okay, let's look at the granularity of the signal. Pulsars are point sources. If they're sufficiently bright, then you could detect them just as point sources. We've been looking for point sources in this region and have found quite a few, but when we can mask out all the known point sources and it doesn't meaningfully change the galactic center excess. But even if the individual sources are not bright enough to be detected as point sources per se, their presence could still lead to an enhanced population of fluctuations in the region of the galactic center excess beyond what you would expect just from Poisson noise, even if no pulsars are individually highly detectable. So by studying the fluctuations in the signal, we might be able to identify a point source population contributing to the galactic center excess. So that's the second direction. The third direction is to say, forget about gamma rays from the inner galaxy. Let's try to look at other locations, other channels, other, other signals in multi-wavelength or multi-messenger probes. And I'll talk about that at the end of my talk. But let's first look at what you can do just with gamma rays in the Fermi data set. The challenge for both of these analyses is that the galactic center excess sits on top of a bright, highly structured background. This comes from charged cosmic rays passing through our galaxy and interacting with the gas in the starlight. This is a picture of that all-sky background, and you can see the galactic center lies within the galactic plane, where there's a lot of gas and a lot of starlight and a lot of cosmic ray populations that we can model in various ways. But we do not have a detailed three-dimensional map of exactly where all the gas, starlight, and cosmic rays are in the galaxy, which makes modeling this background down to the level of noise challenging. And that is the major challenge for both of these analyses. But let's talk about what has been done and what we have learned over the last few years. Okay, so let's look at the first one. How is the galactic center excess shaped? What is its morphology? So one thing that you can try to do in this case is say we're trying to distinguish between a scenario like this. In this upper panel, this is a spherically symmetric excess with a morphology that you would expect from the dark matter halo. In this case, the slope with which the dark matter density rises towards the galactic center has actually been fitted to the data. It is not dramatically different than what you would expect from simulations. On the other hand, a competing hypothesis might be that the galactic center excess traces emission from the stellar bulge plus possibly a concentrated nuclear bulge component at the center of the galaxy. So many of the studies that have been done trying to ask about the morphology have essentially compared this first scenario to the linear combination of this boxy bulge component and a centrally concentrated nuclear bulge component. So over the years, as you read different groups' papers, the preference for one of these over the other has moved back and forth. The early studies using older background models tested bulge models against spherical models and found that they generally preferred the spherical models. The excess appeared to be roughly spherically symmetric. Around 2018, a couple of groups found instead a preference for these bulge-like morphologies. Bartels et al. Built this background modeling framework called SkyFact, which is much more flexible than the baseline models. Basically, they allowed extra degrees of freedom for every pixel on the sky, allowing there to be extra or reduced emission in every pixel, so long as it had the spectrum of protons interacting with the gas. They found that prior to adding these extra degrees of freedom, the fit preferred a spherical morphology, but after adding them, the preference flipped over to this bulge-like morphology. So it at least seems we know from that study that the difference between these two morphologies is something that can be absorbed into modeling of the gas distribution, which feeds into the backgrounds. It's perhaps also worth noting that if you allow this nuclear stellar bulge component, these two morphologies can actually be quite similar in the regions where the galactic center excess is bright and highly detected at high significance. A lot of the differences are in these outskirts, and there the excess is rather faint and the backgrounds are complicated, so it's just hard to tell them apart. So that is the basic reason why this is a somewhat difficult problem to solve. So Bartels et al. Found this in their SkyFact framework, but you might also say, all right, but you have added thousands of extra degrees of freedom to your background model. Are we really retaining predictive power at this point? So another group of these authors wrote a series of papers where they used methods based on modeling the gas density and cosmic ray density within the galaxy with some refinements using hydrodynamical simulations to try to improve the gas maps in the very center of the galaxy. And by this independent method, they also found a preference for this bulge morphology compared to this spherical morphology. So around 2018, I would have said, all right, we see that the preference depends on the background model, but it does seem that the better background models are systematically preferring a somewhat more bulge-like morphology. However, in the last couple of years, there have been another set of papers where people tried to improve the background models along a different direction. These authors have worked with upgraded versions of the Galprop code to improve the modeling of cosmic ray propagation through the galaxy, and they still find consistently a preference for this more spherical morphology for the excess. And very recently—
May I ask a really fast question?
Yeah,
Since there were models that preferred a boxy bulge, I'm mindful that, of course, that our own galaxy has a bar. And therefore, and when people study the galactic bar, they believe it's kind of a boxy bulge model as well. So if the source of this comes from underlying distribution of matter or matter tracking visible matter, wouldn't we expect in this boxy ball feature to see a left-right asymmetry as well in L?
Good. Yeah. So let me just, okay. So
Thank you.
right. So this is meant like this boxy bulge model is based on looking at, I think, like at like red giant stars in our galaxy. So I mean, it's meant to be a model for stellar populations within our galaxy specifically, and you can see it is a bit asymmetric left to right. So when people like ask which is a better fit, this or that, well, one of the things that they're looking at is that east-west asymmetry. So is part of your question, like, would you expect the dark matter to be modified by the dark matter distribution to be modified by the presence of the bar? It's
Yes, also.
Yeah.
Yes,
Right.
also.
So
Thank
yeah,
you.
good. So right. So there are two questions here. One is the empirical, is one of these morphologies significantly more preferred than the other from the data? If you had a clear answer to that, then there would be a question, okay, can we say, for example, if this morphology is clearly preferred, can we say, okay, then it's definitely not dark matter? I think what I would say is that I think we don't actually have an answer to the first question yet, like which of these is preferred from the data. But you are correct that if we did have a clear preference for one of these from the data, there would be a follow-up question of, okay, is this really a good way to distinguish between pulsars and dark matter? As I said, there are production models for pulsars that could potentially give you something spherically symmetric. I don't remember. My understanding is that the expectation from the simulations I've seen is that the inner part of the halo is expected to be pretty spherical, even though the baryonic matter distribution is not. But I don't remember offhand if people have done like a really in-depth analysis of how the bar in our galaxy could affect the overall dark matter distribution and what that would do to annihilation signals. So it's a good question. But my case at this point will be that the background modeling issues are sufficiently severe that we don't actually know which of these it looks like. So DiMauro and Hollis tried to improve the background template space and upgraded modeling of cosmic ray propagation and found a preference for a spherical morphology in contrast to the other studies. This recent paper by McDermott et al. Just compared the best background models from these two directions and found that the best overall descriptions were the ones produced by Hollis et al. In 2021, together with a roughly spherically symmetric galactic center axis. That said, it is worth saying that even those best current models here are still formally not good fits to the data. There are differences between the data and the best models that are larger than Poisson noise. So it is not obvious that as we continue to improve the models, it will remain true that the best overall fit corresponds to a spherically symmetric galactic center axis. So the way that I see the development of this stuff is basically just that there are significant degeneracies between the distinction between these two types of morphologies, bulge-like or spherical, and uncertainties in the background. The uncertainties in the background are currently at a level that it is hard to distinguish these two from each other. But this could potentially be a promising direction if we can figure out how to build background models that are good enough that the remaining uncertainties in the background models are small compared to these differences. But for the moment, I think we don't really know. So the other channel that you can look at is the granularity of the excess. So the cartoon here is that you're looking at the difference between a sort of smooth, diffuse signal with just Poisson noise fluctuations, which is what you would expect if it was coming from dark matter annihilation or from a diffuse process like cosmic rays interacting with the gas, versus the case where you have a collection of bright point sources, in which case there'll be some lines of sight which have pulsars along them or other point sources, and there'll be other lines of sight which don't have any pulsars and point sources along them. So there you expect greater variance between pixels and non-Poissonian fluctuations in your distribution of the number of photon counts per pixel. So back in 2016, there were two main analyses that tried to answer this question of whether the excess looked like it was made of point sources as opposed to being smooth, and both claimed evidence for point source populations. The first category of analyses, which I was involved in, designed a statistical test to try to measure the photon statistics of the fluctuations in the excess. We designed a method called non-Poissonian template fitting, but again, it's basically just looking for increased variance in pixel-to-pixel photon counts. So it's called non-Poissonian template fitting, or NPTF. And the other method was to try to find the point sources individually using wavelet-based methods to try to pick out excesses above the smooth background. And both of us claimed at that point we found evidence for quite a lot of small-scale power in this region of the inner galaxy. So let me talk briefly about the recent results on the wavelet front, and then I'll go on and say a bit more about the NPTF, since that's the line I've been involved in more. So in 2020, an analysis by Zhang et al. At Fermilab repeated the wavelet analysis of Bartels et al. In 2016. And like Bartels et al., they found a lot of evidence of small-scale power and hints of point sources in the region of the inner galaxy. However, since 2016, the Fermi collaboration has put out updated catalogs of gamma-ray point sources in this region. And so Zhang et al. Just compared the results of the wavelet analysis to the latest catalog of identified point sources, which is called the 4FGL. And they found that the vast majority of the peaks identified by the wavelet method were actually already in the latest catalog. So on one hand, this is great for the wavelet method. Back in 2016, before these sources were in the catalog, it was successful at finding a bunch of point sources in this region that hadn't previously been identified. Like, excellent. However, now that those sources have been identified, many of them have actually been identified for many of them, we have counterparts at other wavelengths, and many of them we can say are now actually not at the galactic center, they're extragalactic. They're just along our line of sight to the galactic center. Others we know are definitely not pulsars because we have found the other counterparts. So of these 115 wavelet peaks, only about 40 of them are actually potential members of a pulsar population in the inner galaxy. And the vast majority of these are not identified as pulsars. They're just, we don't know for sure. So that's one thing. The 2016 Bartels analysis assumed that maybe all of these peaks were part of the galactic center excess. We now don't know that a lot of them are not. So the other thing is you can say, all right, but let's assume, fine, most of them are not, but 40 of them, let's suppose, are part of this galactic center excess. Maybe we can test that. Let's mask out all these 40 sources and just all the ones in the U-Fermi source catalog and see if that changes the galactic center excess, if it reduces it at all. So the results of that analysis by Zhang et al. Are shown in the upper plot here. So this is the orange and blue lines are the spectrum of the galactic center excess. The blue line is the spectrum of earlier analyses, masking only the point sources we knew about at that time. The orange line is how things change when you mask all the known sources in the current Fermi catalog, which includes essentially all the peaks found by the wavelet methods. And you see it just doesn't really change. Like it's consistent with no change. That doesn't mean that, now it is possible that some of these sources are part of the excess. This green line is the stacked spectrum of those 40 sources. So they could certainly be contributing at the level of like 10% of the excess. But what this suggests is that the bulk of the emission in the excess should be diffuse or originating from sources that are too faint to be found by this wavelet approach. So the wavelet approach may have found some new source in the excess. It might even have found the bright end of the excess, but we don't really have very clear evidence for that. And we do know that a lot of sources found by the wavelet method probably have nothing to do with the GCE. All right, so what about non-Poissonian template fitting? So as I said, this is where you look at the fluctuation statistics of the pixels in the excess, and you ask, this is a likelihood-based analysis. We model the sky as a linear combination of various templates. And then we ask, all right, how much in the best fit or in a Bayesian analysis, what is the posterior probability distribution for the flux assigned to the different components? So this panel on the left summarizes the results that we got in 2016. These are posterior probability distributions for the amount of flux assigned to various components in the sky in a particular region of the inner galaxy. This orange line corresponds to a population of point sources making up the excess, and this red line corresponds to a smooth component making up the excess. And in our baseline analysis, you can see that the point source population for the excess picked up about 8% of the total flux, and there just really wasn't any evidence for a smooth diffuse component to the excess. The inset is just a sanity check saying if you don't allow there to be any point sources in the excess, does the fit assign the excess to the smooth component? And yes, it does. So that's all consistent. This was, as you can sort of just estimate from looking at the error bars here, This looked like a highly significant detection of point sources. The Bayes factor in favor of the model with point sources was about 10 to the 9. We were also able in this to try to extract information about the properties of the point sources. And as you might expect from the significance of this detection, this suggested the signal is composed of a relatively small number of sources that were just below the detection threshold. However, so in 2016, I would have told you, look, it's pulsars. In 2018, I would have told you, look, we have this evidence and also the morphology evidence that the newest and best background models prefer a bulge morphology. It's pulsars. But in 2019 and 2020, there were a number of studies that suggested that no, this was premature, that there was a bias, and basically the bottom line at the end of the day, looking at this from the vantage point of 2022, is that the background modeling in these early analyses was not sufficient to be able to draw these conclusions, and discrepancies between the background models and the data in those analyses induced a bias, which led to a false high significance preference for point sources. So in these papers, me and my collaborator, Rebecca Lean, and other groups as well, showed that background models used in the original analysis could lead to a significant bias against the dark matter signal. In particular, this means that even if you inject a smooth signal into the data and then try to re-extract it, it will extract that injected smooth signal as being made of point sources. So that means you shouldn't trust it when it tells you that the signal already in the data is made of point sources. You can create newer models that don't have the same obvious failure modes that pass these tests. Bushman et al. In 2020 did some good work towards this. The cost of using those better background models is that the evidence in favor of point sources goes down by a lot and becomes much more dependent on your priors. In Bushman et al. 2020, they found that the Bayes factor dropped from about 10 to the 9 to 10 to the 3 in favor of point sources. In the newest analyses, the evidence for point sources looks like about 2 sigma. Rebecca Lean and I also showed that even if the background models are perfect, you need to be somewhat careful about what assumptions you're putting in about the signal distribution in these models. If you have an overly rigid signal model, that can also lead to a spurious preference for a point source population. And the way that I think of this is that what this non-Poissonian template fitting method is doing is essentially just looking for higher variance between pixels as a signal of the presence of a point source population. But of course, higher variance pixels can also be a result of, if your model is rather bad and your fit is trying to accommodate a model that is rather bad, then higher variance is a good thing because it means you have more room to be wrong. So here are just some plots, just demonstrating the things that I just said to you. This plot on the left is showing an example of how things work with the original background models that we used in 2016. This upper plot is a posterior distribution plot like the one I showed you here. Purple is the point source population, red is the dark matter or the smooth component. This is in a different region of interest, so the flux fraction looks a bit different. But so in this region of interest, the GC is about 3% of the total flux. So then this lower panel shows what happens when you inject a smooth signal that is about twice the size of the galactic center excess on top of the data, and then you run the same pipeline on it. What you would like to see in this case is that this red posterior moves up to the point of the injected dark matter signal. That would tell you that you're correctly reconstructing the dark matter signal, and the point source component should stay in the same place. That would tell you that they're not getting confused. But instead, what you see is that the fit still wants to reconstruct there being 0 smooth component in this analysis, even though there's a smooth GCE component there because you put it in by hand. And instead, it allocates essentially all of that injected signal to the point source component. So that's a problem. That's a bias. It should cause you to have some doubt about the original detection, the original allocation of all this flux to the point source component. These panels on the right are showing, and as I said, you can show that this problem can go away with better background models. So this does seem to be rooted in insufficiently good modeling of backgrounds. This panel on the right is showing an example where we did the same fit as before, now in a smaller region. So the flux fraction in the GC is higher. It's about 15% here. Here blue is the GC point source population. Red again is the smooth or dark matter component. This is the result when we run the standard pipeline on it. As soon as we allowed the excess to have some asymmetry between the north and the south of the sky, then we get this result. So now the red and the blue lines are the flux associated to the smooth components, which are different in the north and the south. And the green and orange lines are flux associated to the point source components, and they're actually consistent with 0. So in this case, what happened is it looked like there was a really strong preference for point sources. As soon as you add 1 degree of freedom, you allow the axis to be somewhat asymmetric, that preference just completely goes away. It drops to less than 1 sigma. So there's not anything mathematically wrong with this MPTF models, but they can give you what looks like a really strong preference for point sources in cases where there are actually no point sources associated with the galactic center axis. All right. So how might we, okay, that seems like an unfortunate situation. How might we improve on it? So there's been some work in recent years to try to go beyond these likelihood-based non-Poissonian template fitting frameworks and see if you can use neural networks to try to extract what's going on with the galactic center axis. The hope here is that in the likelihood-based methods, we have to make a bunch of approximations in order to make the likelihood tractable to compute. Whereas if instead you just do a bunch of simulations and you train your neural network based on the simulations, you might be able to capture information in like multi-pixel correlations, not just what's going on an individual pixel basis. So there are complementary methods by these two groups. I'm not going to go into those in detail, but I will tell you what the answers are. The most recent results from the first approach find that the excess should be less than about 2/3 smooth emission. So they're detecting a sort of 1/3 point source component at about 2 sigma confidence. The second approach finds a point source fraction of about 40%, but with a lower error bar of about 20%. So these are both sort of roughly like 2 sigma detections of a significant point source contribution to the galactic center axis. Now, you might ask, okay, but these neural networks still rely on the not great background models that I have talked about for training purposes. So, and that is a possible source of systematic error that I think we should be concerned about. However, it is true that you can test the result of training the neural network on one set of background models and then applying it to data that was simulated from a different set of background models. And you can test examples like the one we had on the previous page where an asymmetric smooth excess gets interpreted as a bunch of point sources. The neural networks actually do seem significantly more robust than the likelihood-based non-Poissonian template fitting method in these situations. Like they will correctly identify the excess as being smooth, even though it's asymmetric, when the older methods fail to do that. So there is some indication that these methods can do better and can be more stable. And they are still getting some kind of evidence for point sources, but it's not especially statistically significant. These are some plots provided by Siddharth Mishra Sharma showing the results for the likelihood-based non-Poissonian template fitting in the upper panel, and then how things change in the neural network approach on the lower panel. So these panels are showing the distribution of the inferred point sources with respect to flux. And these component intensity plots are like the posterior plots that we looked at before. These plots on the right, those I think are informative. So these are showing the degeneracy between the fraction of the emission in galactic center excess point sources and the fraction of the emission in a smooth component. And you can see that there's a lot of degeneracy here. I mean, the sum of these two components is very well constrained. The difference is much less constrained. And in this analysis, we choose the most up-to-date background models and carefully chosen priors to try to treat these two possibilities on an equal footing. You find that just the two components are very degenerate and basically everything is allowed at 2 sigma. When you go to using a neural network instead, the result is similar. There's maybe even a slight preference for the excess to look more smooth as opposed to point source light. But again, everything is pretty much consistent within at the 2 sigma level. So with up-to-date background models and with these neural network approaches, it appears that we are not detecting strong evidence for the galactic center excess to be dominantly composed of point sources. It may still be composed of point sources, but they would need to be point sources that are fairly degenerate with the diffuse emission. How might we do better than that? Well, one obvious thing is that currently these neural network and non-Poissonian template fitting methods actually throw out the vast majority of the Fermi data. By default, these only look at photons at 2 GeV and higher. This is a choice to reduce backgrounds and to try to have a sample with better angular resolution, which in Fermi data gets better at higher energies. But even above 2 GeV, these analyses also throw out roughly 80% of the photons above 2 GeV. but are due to quality cuts that are imposed to try to maximize our chance of getting actual photons rather than background cosmic rays, and also to pick only the photons that have the best angular resolution. So you might say, okay, that made a lot of sense when we thought we had a 10 sigma detection of point sources. There you only care about systematics, so you're willing to sacrifice statistics for the cleanest sample. But if we think maybe we've got a 2 sigma detection of point sources, then statistics are actually very important. So can we recover these 80% of photons above 2 GeV, and can we use photons at lower energies? So I recently wrote a paper with an undergrad student, Lois Barrowan, who was great and is applying to grad school this year, trying to understand within the likelihood-based methods, the non-Poissonian template fitting, how do you expect the significance of a detection of point sources to change as you change the number of quartiles you include? And unfortunately, the answer that we found is that there's not a lot of room for improvement within at least the simplest version of those methods that have been implemented in public code. So this panel on the right, the y-axis is a measure of the detectability of a point source population, so the expected test statistic in favor of a point source population if it's really there. The x-axis is showing what happens as you go from having only the top quartile in angular resolution to the top 2 quartiles in angular resolution to the top 3 quartiles in angular resolution. These little purple magenta data points tell you about what the expected significance is in our simulations, and the blue stars are showing how you would expect the significance to increase as you added more quartiles if the only thing that was happening was adding more photons. And the little orange pens would expect this significance to fall off if the only thing that was happening was you would making your angular resolution worse. And unfortunately, when you combine these two effects of worse angular resolution but more photons, in a naive way, your expected result is the black points, which are basically completely flat with increasing the quartile. And that's also very consistent with what we see in the simulations. That said, this is the simplest version of the implementation, which at the moment assumes that all photons have the same angular resolution, and the angular resolution is the angular resolution of the worst photons in the sample. So you probably can do better than this. If we can avoid the assumption of a single angular resolution, then it seems like adding more photons should purely be good for you. But you will have to do something a little more sophisticated than the simplest thing in order to get more information out of this data set. The other thing that we may be able to do, especially with these simulation-based inference tools, is use the energy information. At the moment, these analyses are just taking all the photons between 2 GeV and 20 GeV and putting them all in a bucket. If we can use the energy information, use the spectral information, that might allow us to distinguish different components better, and it would also just correspond to having many more photons. So my group has some work in progress to try to use machine learning-based methods and probabilistic programming to try to better quantify the uncertainties and understand the degeneracy between the modeling of different background and signal components. Of course, the other thing that you might do is say, well, okay, gamma rays near the inner galaxy seem really hard. Let's look at other targets or other channels. So you can say, all right, if this is dark matter, maybe we would see a signal in direct detection or at colliders. That's been studied back in 2014. Unfortunately, it's very model dependent. Like that you can come up with models that a signal should be right around the corner. In direct detection, you can also come up with models that you're very unlikely to see them in the near future. So the most model independent way to exclude or possibly confirm a dark matter signal would just be to look for the same gamma ray signal in other systems. The cleanest systems are dwarf satellite galaxies, but unfortunately the sensitivity is not quite good enough for exclusion. This is a nice paper by Cohen et al. From 2021. These blobs, these gray blobs here are cross sections that have been inferred for the Galactic Center XS in gamma rays. You can see this 2 × 10⁻26 number is right around here, I told you about earlier. And then each of these lines and shaded regions are supposed to be exclusions from other channels. The dwarf galaxy bound, older versions of bounds from dwarf galaxies in the Milky Way was sort of down around here, which seems enticing. But the latest analyses actually tend to give somewhat weaker constraints. And partly that is because of improved treatments of the uncertainty of the dark matter density in the dwarfs. Now you might look at this and say, aha, but this whole region is ruled out by this gray constraint, or by this, with the gray constraint is M31 radio and the green constraint is antiprotons. But there are actually claims of counterparts in both of these channels, and there's been a recent update to this M31 study, which gets significantly weaker constraints as well. As I mentioned, there are claimed counterparts in M31 radio, gamma rays, and in antiprotons. None of them are yet especially convincing, but they make it hard to rule things out. And I'm happy to say more about that in the questions if people are interested. You could ask, okay, but what about pulsars? If we're going to, what about looking for pulsars and other wavelengths and understanding how plausible the pulsar scenario is? So there's been considerable debate in the literature just about whether you could get a pulsar population that is what we need to make the signal. In particular, if you really need a really large number of really faint sources, then just explaining how to get that many pulsars in the inner galaxy could be challenging. So a key question here is just what is the expected luminosity function that we expect for these pulsars? How many bright and potentially detectable sources should be visible for every unit of flux or every unit of fainter sources? So there were some recent papers. Zhang et al. Actually quoted an estimate that you would need about 3 million pulsars to make the excess. And if that was true, that would seem quite hard. There are production mechanisms that people have proposed that could get you about 100,000 millisecond pulsars in the galactic bulge. 3 million may be difficult. However, it turns out that assumes a very faint luminosity function for those sources. At the other end of the spectrum, the earlier non-Poissonian template fitting studies found a preference for all the sources to be right at the threshold, needing only about 1,000 total. But as we know, those studies were biased by a bad background model and probably were preferring brighter point sources than are really there. So I wrote a paper with a former undergrad student, Jack Dinsmore, who's now at Stanford, where we just considered a range of luminosity functions in the literature and tried to understand what could be consistent with current observations, what could still explain the galactic center excess, and how many pulsars you need. And the one-line answer is it's fine. Like there are simple luminosity functions that are similar to what we see in other systems that need about 10,000 pulsars total and predict very few detected high significance sources. This lower panel here is showing under these models the number of point sources that you would expect to detect in Fermi's latest catalog. The different colored data points correspond to different models. The black dashed line corresponds to the total number of possible sources that are actually in Fermi's catalog. However, quite a lot of these relatively faint sources are flagged as having some kind of problem or uncertainty with the identification. If you look only at the unflagged sources, you get this dotted this dotted line here. So just as an example, these black data points are the luminosity function that we would have inferred from those early non-Poissonian template fitting analyses. And you see that they would actually predict that there should be a lot of sources right at the faint end of the 4FGL catalog. So this would require that basically all the sources that we have seen at this brightness in the 4FGL catalog are part of the excess. And furthermore, that all the flagged sources are actually real. That seems unlikely. But we already know that those sources are likely to be spurious, that when we use better background models for this, we get a preference for fainter sources instead. There are some other luminosity functions that seem somewhat in tension with the observed number of sources, but again, there are many that are completely fine. It's perhaps also worth noting that as in this paper, we showed that if you could improve the sensitivity down to the level of being able to sort of probe like levels of like 1 or 2 photons per source, which you can maybe do with these neural network methods, they claim sensitivity at that level, then in those cases, you should be able to resolve at least 30% of the excess, which is perhaps relevant given that these neural networks seem to be claiming at 2 sigma significance, something like 30% of the excess showing up in point sources. Okay. The last thing I'll say is that, of course, you don't need to focus on gamma rays. Typically, pulsars also emit in radio and X-rays. For radio in particular, we expect there to be a much larger expected number of photons than in gamma rays, and we could try to detect the pulsations. And there was a forecast done back in 2016 that the Meerkat telescope, which is currently operating, could see tens of pulsars from this population, and the next generation big radio telescope, the Square Kilometer Array, could potentially see hundreds. There have also been some recent studies identifying X-ray sources in Chandra data that could be promising pulsar candidates for multi-wavelength follow-up. So there is some work to be done on that front as well. All right, so summary at the end of the day, the galactic center excess seems to be a robust feature of the central region of the Milky Way. The leading explanations remain a population of pulsars, especially millisecond pulsars, or an exotic signal from dark matter. If we model the excess as a combination of a population of point sources and a smooth diffuse component, There have been claims in the past, including on papers that I was on, that there was a strong preference for most or all of the galactic center X's to be attributed to point sources. But we now think that those claims were overly strong, were biased by bad background models. With more sophisticated methods in background modeling, that preference is now quite mild. I would say that it is at the true signal level. The detailed morphology extracted for the GC is also a promising way to distinguish hypotheses, but recent work has demonstrated that that is also very sensitive to the choice of background model, and it is not clear if we have converged on that front. We're still at the stage where improvements to the background model can flip the preference back and forth between different morphologies. And there's active work in progress to improve both analysis methods for inner galaxy gamma rays and searches for counterparts of other wavelengths, and I would be very happy to chat with anyone who has ideas. So thanks very much, and I'll take questions now.
Yep. Thanks, Tracy, for this very excellent talk. So questions?
Hi, Susan.
Oh, yes. Thank you very much. I'm very curious. Thanks for a nice talk and review. I'm curious what actually sets for the Fermi-Lat's point source detection threshold, and whether future gamma ray missions might be more sensitive or whatever. I mean,
yeah. So of course it's a combination of angular resolution and just effective area, as per usual, right? So Fermi's angular resolution. So there's a trade-off here, and it also depends on the spectrum of the sources. So the general rule for all of these source populations is that they get brighter at lower energies. Fermi's angular resolution also gets dramatically worse at lower energies, below about a GeV. So you go to lower energies, all your sources are brighter, but it's much harder to distinguish them from the background. So there have been proposals to do future missions that focus on the lower energy band, like the MEV to GeV band, and maintain better angular resolution in that regime, with the hope that then you could see some of these sources that are difficult to detect in Fermi, even if you have like overall worse effective area than Fermi. You just like win by going down the lower energies where there are more photons while trying to keep the angular resolution somewhat intact. Like, because I mean, with Fermi, it gets really bad. Like by the time you get down to about half an MEV, half a GeV, the angular resolution is like 3 or 4 degrees. So it's hard to find point sources in that regime, especially if you're close to the galactic center and everything's very crowded.
Great. Okay, well, that's very clarifying. Thank you very much.
I guess I will just say one other thing, which was that as well as, just getting better instruments with better angular resolution, of course, the other thing that you can do is just try to do better analysis methods. And the scary thing here is that your background modeling becomes important, but I mean, these neural network methods and the non-Poissonian template fitting methods in principle do have sensitivity to point sources down to sort of the absolute cutoff. The theoretical cutoff is where the point sources are producing significantly less than 1 photon per source. But I mean, the neural network methods actually claim to have sensitivity down to that scale where you're producing like 1 or 2 photons per source, not at the level of you can find the individual source, but at the level of you can say something about there being a population there. Mm-hmm. The concern, of course, is that if you don't understand your background, then it's very easy to imagine, causing biases when you're relying on trying to be able to see things at 1 or 2 photons per source. But if you could see that, like even in the most pessimistic luminosity function models we looked at, you would expect to be resolving like 30% of the flux in the excess. So better analysis can to some degree make up for a lack of better instruments. But of course, better instruments would be great too.
Well, I think as a cross-check, it would be very powerful to, as you say, determine some fraction of pulsar population, and then along comes some, I guess the MEV
and actually
study. And
that would be awesome. Yeah, I mean, the other thing to do would be to try to spot if you could see the pulsars like in radio or in X-ray and then cross-correlate them with hotspots in the gamma rays. That would also be a nice check. You use the better angular resolution of the lower energy instruments. I see Varun.
Thank you very much.
Hi, it was a very clear and easy to follow talk. Thank you for that. My question is this: how well do we know the dark matter distribution? So you're basing it off of the n-body simulations that we expect in a pebble profile, if you had structure to dark matter, can we replicate something like what we see from, let's say, for example, point sources or whatever? Can you add structure and then maybe?
Yeah, good.
Yeah.
So let me say, so the first question, like, how well do we know the dark matter density distribution in the galactic center? I mean, we don't very well. So, if this was actually a dark matter signal, even with our uncertainties on the galactic center excess, the galactic center excess would be by far our best measurement of the dark matter distribution in the inner galaxy. So, right. So what's currently being done when people is that people say, okay, let's assume basically a spherically symmetric distribution with a power law slope, and then they fit the index of the power law slope from the data, and you get something that is a little steeper than classic NFW. And then we say, yep, that is within the wide band of possibilities from simulations with baryons in them. So like this is not a case where we have a sharp prediction from the simulations and then we observe that the data matches the simulations. It's not like that. It's like there is a wide range of possibilities. The data matches something that is probably within that band of possibilities. So the question about like, what about I think you're asking about could we get something that looks like point sources just from dark matter? So there was a study on this by Lisa Randall and collaborators a few years ago, and it's possible, but it's really hard. Like you can't do it in CDM. You can maybe do it if you have some like significantly interacting dissipative dark matter that forms chunks of dark matter. But the reasons why it's hard to do in CDM is, so there are a few. One is you expect substructure like clumps of dark matter to get disrupted towards the center of the gap. So, okay, so if you want it to be all point sources, what you want is there to be like little clumps of dark matter where the annihilation is efficient within those clumps and most of the power is coming from annihilation within those clumps. That's hard to reconcile with the data, because then you would expect the rate at which the signal rises towards the galactic center to just scale with the density of these clumps, not with the density of the background halos. So if the annihilation is mostly happening in the smooth halo, the annihilation rate scales with the density of that halo squared. So like the actual rate of increase towards the galactic center looks like an NFW profile squared. So it's hard to understand why the density of the clumps would go up that fast towards the center, especially since naively we would expect the clumps to get more disrupted as you get close to the galactic center. So getting a morphology that is steep enough with like little dark matter clumps is quite hard unless you've got some way to like really make a lot of clumps and hold them together in the face of disruption, which is why you need like strong interactions and you need a dissipative interaction to get very dense little clumps of dark matter. So like it's possible, but it's not what you expect from CDM. What you would expect from CDM is that the inner galaxy signal is dominated by the smooth halo. Now, the place where substructure does become really important is that there's a claim of a possible counterpart signal from the outer halo of the Andromeda galaxy, and this one is not as high significance and there are significant uncertainties on the spectrum. But if it was there, it basically has to be coming entirely from substructure in the outer halo of Andromeda. You need a boost factor from substructure that is about a factor of 20 over the smooth halo to get, which is consistent with expectations in CDM, but like you would need that level of boost. So yeah. So like that's a place where substructure in the halo would be important.
So could you also look for this in dwarf galaxies of the Milky Way itself?
Yeah, so people have done a lot of searches for just a signal like this in dwarf galaxies. So yeah, like this dashed line here is the latest limit from the dwarf galaxies. So everything above this is excluded. Unfortunately, most of the galactic center excess parameter space is below that. So yeah, the problem in dwarfs is now that said, that's marginalizing over uncertainties about the dark matter density in dwarf galaxies. So if you had a better handle on what's happening with the dark matter density in dwarf galaxies, maybe you could move this line back down. Like there's another dwarf galaxy line down here, this one, which excludes a lot of the GC parameter space, but that's an older analysis using less data. But I think with less expansive assumptions for what the dark matter density in the dwarf galaxy could be. So if you can narrow that error bar, you can probably improve the dwarf galaxy constraints by quite a bit, or Or if, you know, LSST tells us about a whole bunch of extra dwarf galaxies, then maybe there's something that could be done there too.
Thank you very
Does
much.
that help?
Yeah. It's very useful.
But yeah, I will say, like, yeah, there was a lot of interest in could you get a bunch of point sources with dark matter a few years ago, when it really seemed like we had, you know, like a 8 sigma detection of point sources in the excess. Now that I believe with the latest background models, it's more like a 2 sigma detection of point sources in the excess. There's less of an incentive to say, you know, what could explain something that looks like point sources in the excess. But my recollection from a few years ago is in the inner galaxy, if it's dark matter that's not like strongly interacting dissipative dark matter that makes a disk that then fragments, the expectation is pretty clearly that you expect the smooth halo to dominate. And Addie Evans.
Eddie Evans.
Yeah, hi. Thanks for the talk. My question is, in the analyses where people are saying, okay, I have my Galactic Center excess and it's this % diffuse and this % point sources, do people do tests where they say, okay, it's this % point sources and it's all due to millisecond pulsars, and you know, like the spectral morphology or the spectral shape looks like this, the spatial morphology looks like that. Let me subtract that out. And do I still get something that looks like kind of like the canonical WIMP dark matter signal? Does that make sense?
Yeah, I think so. So let me say a couple of things. So people have tried to do, right. So good. People have tried to do a situation where they fit the excess, say that's all millisecond, like fit the excess with the bulge model, say that's all millisecond pulsars. That like Abazagian and colleagues did this in one of their papers, building on the background models where they find a bulge morphology is preferred. So people have done the situation where they fit the excess with the bulge morphology, say, okay, assume that everything that traces the bulge morphology is millisecond pulsars, subtract that off, ask how much room there is for a dark matter signal. In that case, with that background model, they didn't find that there was evidence for like a dark matter signal, and they were able to set strong constraints on the dark matter component. But that works on the assumption already that like you can subtract off everything that in their scenario fits the bulge morphology and attribute it to millisecond pulsars. So yeah, usually So I mean that is a thing that you can do, but it, as I said, so you know, if you did exactly the same analysis with one of the background models that instead prefers like an NFW-like morphology for the excess, and so you know, if you allow both in the fit, the bulge morphology picks up a very small coefficient. Then if you subtract it off, yeah, then there'll still be a lot of evidence for an NFW-like morphology. So at some level there, it's just kind of a question of what does the fit prefer for the morphology. So let me say a couple of other things. So like energy information. In a lot of these studies, people actually aren't using energy information to separate the components at all. Like we're just using one big energy bin from 2 to 20 GeV. I agree that using the energy information could potentially be pretty valuable in disentangling the two. I mean, just as sort of one simple thing, suppose there was a millisecond pulsar component and also a dark matter component. If we go like way back all the way to here, you know, you can see that like the dark matter spectrum in these models is actually noticeably like has less power at low energies than the millisecond pulsars. So like if there were two components, you might expect to see a morphology that is like more millisecond pulsar like at low energies and less millisecond pulsar like, you know, like more dark matter like at high energies. Would be one possibility. So I mean that it might be possible to use the energy information to tease out more stuff. The reason that hasn't been done yet is just a technical thing. I know that Ben Safdie and his group have been working on how to incorporate that into like the likelihood analyses of the non-Poissonian template fitting for years. The problem there is just that the whole thing that makes the non-Poissonian template fitting simple is that you abstract out the information about where exactly the point sources are. You sort of just like marginalize over the positions of all the point sources. But if you want to put in energy information, you don't want to do that because it's important that the point sources are in the same point at different energy bins. So now you can only do that abstraction over the position of the point sources after you've tied the information together for all the energy bins. Like you don't get to do it independently for each energy bin, which is what usually simplifies the calculation. So it's just hard. I think Ben has a way to do it, but last I talked to him, it was just very slow. So that said, if you're going to do these simulation-based inference methods instead, then it seems relatively easy because it's easy to just simulate the point sources being in the same place across all the energy bands. That is how you would do the simulation by default. So that's the other thing. So energy information may be helpful. I guess what I'll say, my group has been doing some initial tests where we try to simultaneous. So let me say one other thing. The tests where people have been testing the morphology, the studies where people have tested the morphology and the studies where people have tested the photon statistics are largely disjoint from each other. So, in general, people for doing the photon statistics tests have just assumed some morphology. Like we've done some checks along the lines of, okay, what happens if you replace the NFW template with the bulge template? Does that change the answers about the granularity? And found that it didn't, but it's not quite the same thing. But my group, an undergrad student working with Yuqing Wu, who's at Imperial and I think is also applying for grad school this year, wanted to do some runs where we sort of tested, basically had 4 templates to be tested against each other, like something that looks like the bulge and is smooth, something that looks like the bulge and is point source like, something that looks like dark matter and is smooth, something that looks like something that looks like NFW that is smooth, something that looks like NFW that is point source like. And she had this is super, super preliminary, okay? So don't take this too seriously. It's both super preliminary and super low significance. But the first run that she did like that, the fit was the best fit was 30% bulge point sources, 70% smooth NFW. And I was like, you've got to be kidding, right? Because this is everyone's dream scenario where there's both a pulsar population and a dark matter. That said, when I say it was the best fit, the Bayes factor in favor of this over, say, everything looks like NFW was 2. So, we're talking about a 1 sigma preference here. So, don't, and also it was preliminary. So, don't take it too seriously. But yeah, but I mean, that is a kind of test that we can do. I guess my worry a little bit is that if our detection of point sources at all is sort of at the 2 sigma level, then when you try to start breaking that down further, you're going to find that you don't have a lot of statistical significance. Right. But that might be a regime in which if we can recover some of the photons that we are currently blithely throwing out, then maybe we could do something there.
Okay, thank you. That was very interesting.
Very, very good question.
Yeah. Are there any more questions in the chat or anyone?
I know you said you wanted to finish on the hour strictly, and I see that we're there. So I'm sorry I went a bit over time in the talk. But...
No, it's fine. Yeah. I think there is no more question. In that case, let's thank Tracy for his excellent seminar and for answering all the questions. So we will meet next week.
And if people have either other questions or thoughts for follow-up, or why are you doing your statistics this way? This is crazy, or better ideas for how to go after this, feel free to shoot me an email. I would be happy to chat more because, yeah, my current take on this is that this is an interesting high significance signal, and unfortunately, all the methods that we've tried to figure out what it's currently doing are sort of giving us somewhat inconclusive results at the moment. So, yeah. It may be that we just need more data, we need to find the pulsars in the radio, or, the GAPS balloon might find an anti-deuteron next year, and then we all get convinced that there's something strange, that, there's something exotic going on. But it may be that we just need more information, but I'd be definitely interested in ideas. Okay, well, thanks again. Thanks everyone for the good questions.
Thanks for the great talk.
Thank you.
Thank you very much. Bye-bye.
Bye.
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 Thank you.
Bye.